All right, let's take a look at a couple questions and see if we can apply the concepts we learned in the previous screencast. The question here is, write the voltaic cell reaction and sketch a cell, so that's the whole 9 yards, showing all the cathode, anode, etc., in which magnesium metal is oxidized to magnesium ions. So I'm telling you that Mg is oxidized to Mg2 plus. So that means 2 electrons would be lost. This is solid. That's aqueous. Copper ions are reduced, so it's Cu2 plus, aqueous. Pick up those electrons, give you Cu solid. So that's reduction. This is oxidation. Top reaction is oxidation. Bottom is reduction. The question is that you have to identify the cathode, the anode, the direction of flow on the sketch. So first of all, you have to write down the voltaic cell reaction. So this is the reaction, the half reactions, and you have to add obviously so that you get Mg plus Cu2 plus, giving you Mg2 plus copper. Since it was a 2 electron change, we didn't have to do anything special to balance it out. But if you were to show this in a cell representation diagram, you would say that magnesium is becoming Mg2 plus. The concentration is not given, so I'm just going to say aqueous here. Of course, I have my salt bridge, and then the copper 2 plus, which was in the aqueous phase, is going to get deposited as the solid. What occurs at anode is oxidation, or another way to say the same thing, oxidation occurs at anode. That means this electrode is the anode, left side. This electrode is the cathode. So we have the anode and the cathode. Direction of the flow, as always, is going to be from anode to cathode. So we have done that as well. Done, done, and done. And they also want me to sketch a cell. So this is my representation. Let's see if I can also quickly make a little miniature diagram. Here are my 2 electrodes. That's my magnesium. So in order to keep it consistent, let's keep a magnesium nitrate solution. I have copper, and that is dipped in copper nitrate solution. Of course, I have the wire, I have the voltmeter, and I have a salt bridge. So this is the salt bridge. That's the anode. That's the cathode. And that's about it. We have represented everything that we required. Now realize that if you have a positive standard cell potential, so if your E0 cell is a positive value, then that corresponds to, that implies that the cell would be spontaneous. And the reason that we say that is because in that reaction, your E0 cathode minus E0 anode, which basically gives you the E0 cell. Realize again, recall, we discussed this in the previous screencast. Both of these are reduction potential values. Both of these are reduction potential values. And so this basically talks about a situation where the E0 anode will be more negative, and so that would mean that the metal, which has a tendency to go through oxidation, is situated at the anode and has a tendency to give up electrons and remain in the ionized form, which the electrons basically, which then travel on the other side through the wire and go through a reduction reaction. So one can say that if your E0 cell is positive, we have a spontaneous redox reaction, and we know that from the previous chapter on thermodynamics, that delta G0, if that value is a negative value, we know that then we have a spontaneous reaction. So these are two things. E0 cell has to be positive, delta G0 has to be negative. So hopefully you can envision that perhaps there is some kind of a relationship between delta G and E0 cell in case of a redox reaction. Likewise, we also saw earlier in the chapter on thermodynamics that delta G is negative RT ln K. So it's also related to the equilibrium constant. And that would mean that the equilibrium constant and the electrode potential are also related. So one can hopefully see that if we are thinking about a spontaneous reaction, for that delta G should be negative, delta, or not delta, but just E0 for the cell should be positive, and the K values that you get should be more than 1. And if you are thinking about a non-spontaneous reaction, that means, of course, just the opposite of this. So non-spontaneous reaction would mean that delta G should be positive, E0 cell automatically will be negative, and the K values will be much lesser than 1. Now, we can actually derive a relationship between delta G and E by returning to the definition of potential difference. Potential difference is basically a measure of the difference in potential energy per unit charge. So let me write that. So what I just said is that potential difference is the difference in potential energy per unit charge. So one can say that this is the potential energy difference is essentially joules per coulomb. Okay, now the potential energy difference is nothing but the maximum work that can be done by the system on the surroundings. So since this potential energy, since that represents the maximum work that is doable by the system, so this has to be the work done by the system. So if it's a battery in question, then it's the it's a battery, which is the system, by system on surroundings. And so we can say that the maximum work done is equal to negative Q E0 cell. And the reason why you can say that is because the potential difference E is nothing but J joules over C, the charge. The charge can be represented by Q. This can be represented by Q. And so that automatically means that the E0 cell times the Q, and we are using a negative sign because this is work done by the system. So recall from Gen Chem 1, work done by the system always is a negative sign. Now, you can quantify this charge that flows in an electrochemical reaction by using a Faraday's constant, which is given by F, and that's basically the charge carried by a mole of electrons. So 1 mole of electronic charge is 96500 coulombs, and you can get that very easily because 1 mole of electrons means 6.02 times 10 to the 23 times 1.062 or 602 times 10 to the negative 19 coulombs. So Faraday is a value that you get in coulombs per mole. Okay, so if you can determine if your total charge is basically Q, that will be some integral value of the Faraday. And so you can substitute, if this is equation 1, you can substitute equation 2 into 1. And so your maximum work is nothing but negative NF E0. And if you have those values, the E0 cell, you can determine that. So now hopefully you can see that if the E0 cell is a positive value, that would automatically mean that the maximum work done, which is the useful work, is going to be a negative value. And from chapter on thermodynamics, hopefully you can recall that the maximum amount of work done by the reaction is nothing but delta G. So you can now substitute the given equation. You can replace the W max by delta G, and you can say that delta G0 is equal to minus NF E0 cell. Okay. The question this hour is calculate the value of delta G and the work done on the circuit for the reaction. So the reaction that's given is magnesium plus copper gives you magnesium plus copper solid. And this is taking place in a voltaic cell that produces 2.71 volts. So you have to determine delta G. So that's pretty simple. You can just say it's NF E0. E0 is provided to be 2.71. Notice magnesium is becoming Mg2 plus, copper is becoming Cu2 plus, so the net electron change here is only 2 electrons. Faraday has a constant value of 96500. We are going to plug in the numbers and get your answer. And this number comes out to be negative 523030. And notice in terms of units, N was the number of moles. Faraday was coulombs per mole. So the mole and mole is going to cancel off. E0 cell is joules per coulomb. So the coulomb and coulomb will cancel. Delta G is a form of free energy, and the units on the right hand side are also in joules. So we're good. You can also write it as 523 kilojoules or 5.23 times 10 to the power of 5 joules, however you want to. But realize it's a negative sign. That means that the cell is going to be spontaneous. So if somebody asks you, how do I predict spontaneity? Well, you can take a look at delta E0. If that is positive, then that would automatically mean that delta G should be a negative number, and that means that the way our anode and cathode are set up is fine. Otherwise, we have to invert it. Now, the slide basically talks about a lot of information that I've already given you in the screencast, which is the previous screencast. But there was one thing that I wanted to get your attention to, and that is the older convention where E0 cell was just taken to be a combination of the cathode and the anode. And the reason why they did that was they said, well, in a battery you have a redox reaction that's taking place. So it's half reduction, half oxidation. It only makes sense to basically add the reduction potential at the cathode and the oxidation potential at the anode. And so they came up with this, formula that you can simply add the two numbers. You're simply adding the reduction and the oxidation potentials, and you're going to end up with the E0 cell. But then, like I said, lots of problems occur. People would get confused whether they're supposed to use oxidation or reduction. So they then came up with a common, sort of a convention where anytime electrode potential is referred to, they would that would automatically mean that we are talking about a reduction value. Now, one thing that I want you to understand is that these electrode potential values, they basically provide, it's a reflection of the tendency to go through this oxidation or reduction reaction. So if it's a tendency, whether you have 1 mole or whether you have 2 moles, it doesn't matter. This is something which is an intrinsic property of that particular element. And so if you run the reaction and let's say you're balancing it out and you now wanted to multiply the reaction by 2 or something like that, that does not mean that you're going to multiply the electrode potential also, because that reflects again the tendency to go through a certain reaction. What you may do, however, is that since oxidation and reduction are opposite of each other, if your oxidation potential is, let's say, 1, that would mean that the reduction potential is going to be -1. So in a sense, one can say that the oxidation is inverse of the reduction value. And so if I plug that information here, I can say that whatever is the reduction potential at cathode minus whatever is the reduction potential at anode, and that is going to give me your E0 cell. And that, by the way, is my modern convention. That's my modern convention. So just to kind of give you a flavor, I have here the zinc air battery where zinc is getting converted to zinc oxide. So you can see that it's going to Zn2 plus. That means it must have lost the electrons, and hence that is going to behave as your cathode. That means oxygen, which has gained O2 negative, is what you get right over here. It leads to a reduction reaction at the cathode. Notice that the E cell for this is given to be positive value, and that automatically tells you that this battery will work because the reaction is spontaneous. So realize that if you're given some information about oxidation and reduction, and maybe you may not be given the E0 cell, you would be able to calculate it by simply using E0 cell. Use the reduction potential values as cathode minus anode. As long as these are both reduction potential values, you would be able to read if the E0 cell is positive or negative, and on the basis of that, you can predict whether or not the reaction is spontaneous or whether it requires reversibility of or polarization of the positive from the negative. Now, like I said earlier, this is just a picture depicting the SHE, the standard hydrogen electrode. So that's your HCl, the 1 molar HCl, that's your platinum electrode. And we are pumping in the hydrogen gas. And this has been randomly marked to be at 0 volts. So what we discussed in the last screencast, this is a picture diagram to show how it works. Then, like I discussed in the same one, you can have a combination of zinc and hydrogen electrode and copper versus hydrogen, and you would be able to pick your cathode from the anode on the basis of the SHE that you are getting. If that number essentially is a positive value, that would mean that that cell, the way it has been set up, is fine. All right, the question is calculate the cell potential for the reaction Fe3 plus 2 iodide gives you Fe2 plus and iodine. And you have to get the potential values from the appendix or from rather the book, the table in the book. So hopefully you can see that here we have Fe3 plus giving you Fe2 plus. And so I'm looking for that value. Fe3 plus and Fe2 plus. So the reduction potential value, the equation here is Fe3 plus an electron gives you Fe2 plus, and the value for that is 0.77 volts. And then we have iodide, which is becoming iodine, So hopefully you can see that 2 electrons are being lost in the process, and you have to put in a 2I minus in front of the reactant, and of course the reduction potential for this one, so written as I2 plus 2 electrons, giving you 2I minus. That value, the E naught, is given to be 0.54 volts. So hopefully you can see that Fe3 plus is gaining the electron, and I minus is losing the electron. And so in order to get the complete equation, you will have to multiply the top equation by 2. And so that gives you your overall electron change as 2 electrons, which is going to get cancelled, and you will be left with 2 Fe3 plus 2I minus gives you 2 Fe2 plus I2. So this is oxidation, and this is reduction. So what we did in this case was we basically took a look at, in terms of the reaction, whether the reaction makes sense in terms of the charge increase in oxidation number and decrease in oxidation number. And like I said, another way to see that in terms of electrical potential values is that you take a look at the number itself. More positive is the number that basically tells you that that particular species will have a greater tendency to go through the gain of electrons, since these are reduction potential values. And so this means that the Fe3 plus is the one that will gain the electrons. So this is the one reaction that occurs at cathode, and the iodine reaction is the one that occurs at anode. So now if you were to determine the E naught cell, you're just going to say E naught cell is E cathode minus E anode, and you plug in the numbers. So 0.77 minus 0.54, and that value comes out to be 0.23 volts. It's still a positive value and tells you that reaction is a spontaneous reaction, and it will generate an overall potential difference of 0.23.